Good morning to all of you. So, so today we are going to learn about photoelectron spectroscopy. This is the first class on photoelectron spectroscopy, a technique which is genesis of which lies in the photoelectric effect, which was discovered long back by Einstein, and even before Einstein, somebody else also observed it. I think Hertz. Yeah. So you are familiar with this picture if you refer to my first semester classes on quantum mechanics. Even at that initial stage, I had introduced this thing about photoelectric effect, where hello, can you hear me? Yeah. Okay, so what do you see here? Hello, आवाज आ रही है मेरी? Mic is on. So before I lost the connection, I was talking about the genesis of photoelectron spectroscopy. So its origin lies in this photoelectric effect, which was discovered long back. You know the Einstein's theory. So yeah, this that was it. What you can see here is that yellow colored wave, that is the light wave, striking the surface of a metal, which is the cathode in this particular tube like arrangement, and the electron, as the photon as the light falls on this thing, the electron is ejected out. It is the electron that is traveling in this direction and hitting this anode, captured by the anode, travels towards the anode. So this was found to be characteristic of a metal in initial days, that only certain wavelength of light, only a certain, if you reach a certain beyond a threshold value, एक मिनिमम लिमिट है, उसके ऊपर आप एनर्जी देते हैं, एनर्जी वाला स्क्रीन इज नॉट शेयर्ड. Just a moment. Screen. Oh हाँ भूल गया. So now you can see that. अब दिख रहा है ना? हाँ. ओके. सो वही था जो फोटो इलेक्ट्रिक इफेक्ट आप पहले से जानते हैं. We have also referred to this effect when starting the quantum mechanics in first semester. So it was the one of the things that only certain, when you reach a certain threshold value of this frequency, only then the electrons start ejecting out. Okay, any any frequency which has lower, any frequency of light that is lower than that threshold value, that will no matter how many such waves you put on the surface, the electrons won't eject out. So this ejection of electron from a surface when the light impacts on it is called photoelectric effect. And so the photoelectron spectroscopy is also, the electron that is ejected is also called photoelectron, electron that ejects out as a result of a photon striking the surface is called a photoelectron. And the spectroscopy that we are going to talk about is also based on that analysis of that analysis of the kinetic energy of that electron that has been ejected. So you analyze the kinetic energy of electron and you get a lot of idea uh, about the bonding, about the orbitals in the molecule, in the atom, in the solid matrix, in a solid crystal. Okay, so this technique is widely applied for understanding the energy of orbitals, the nature of bonding, etc. And so we are going to as we have so in before we move on to the actual spectroscopy thing, this is the schematic of what we know about photoelectric effect. So that idea has been illustrated here, which I was telling you just a while back, that you can see here. This is the surface of potassium, and which requires energy of at least 2 electron volt to eject the electron, and it should come from one single light wave, like one single photon. So when you are having a red colored light 700 nanometer which has only 1.77 eV of energy, it falls on the surface and nothing happens. You might increase the number of such photons, red photons falling on the surface, but still nothing happens. Increasing the number of photon in classical sense means that you are increasing the intensity, and so by classical wave theory the energy per unit area should have increased, but it doesn't happen like this. But still there is no. So this is the point of difference that was understood early on, and the quantum mechanics developed from there. So that's but once you cross this threshold of 2 electron volts, so a green light of 550 nanometer has energy of 2.25 electron volt. So if it made to fall on this potassium surface, the electron, you see the green one, this is the electron which is being ejected out, and it is ejected with a certain velocity. It carries it starts. So 2 ev is the electron, just take away the electron. Rest of it, you have 0.25 ev is extra, and that has been converted into the kinetic energy of the electron. Similarly, if you look at the blue light, which is 400 nanometer, violet light 400 nanometer, which is 3.1 ev, so it is even 1.1 ev extra that you are giving it. So only so it is crossing that beyond the threshold value, so the electrons will be ejected, and the rest of the energy, that is 1.1 ev, will be its kinetic energy. So it moves with a much higher velocity, which is shown over here, 6.2 into 10 to the power 5. So it is, so this is the kinetic energy that is analyzed in the photoelectron spectroscopy. And as you know, if you plot the kinetic energy versus frequency of the incident radiation, for imagine we started with the potassium surface. So if you take the potassium, the previous slide that we had, so if you have frequency of light, you are having different frequency of light starting from the smallest possible frequency to highest one. Then you can see here nothing happens till you reach here 2 ev line, and then you can see, as you increase the frequency that we have seen from starting from red, nothing was happening, green, then blue, violet. So the kinetic energy of ejected electron is uh, goes on increasing, and if you take those data points, plot a graph, it will appear to be a straight line like this. So you can also see that if you change the nature of surface, such as if you have sodium metal, rubidium, then the depending on the orbitals in which it is there, depending on the nuclear charge that it has, the threshold value has changed. The energy required to take away the last most loosely held electron has changed, and this is now in case of sodium it is higher, in rubidium it is less because it's larger in size, down the group. So every metal has a different threshold value, a different value of this particular energy which is required to take away the electron. So that's, and you always get a linear kind of graph which has a constant. You can also note that no matter what is the nature of the surface, the slope is always the same. So as I told you, it is the h mu which was converted into kinetic energy. H mu must be equal, account for both the things, energy, that is the ionization energy plus the kinetic energy of photon. So when you are plotting this ionization energy, actually it is the gaseous phase thing. The metal surface, it is replaced with what we know as the work function, which is phi. Ionization energy replaced with phi, the work function, because it is now uh, crystal lattice. You have electrons, sea of electrons in which the cation lattice is submerged, and from that interaction you are taking away one electron. So that is different from ionization energy the way we have understood in previous early chemistry classes, where you were just talking about a gaseous atom, isolated atom, and the energy required to take that away. So this is a system where you have lot of atoms packed together in a tight in a close packed structure, and so the energy required would be different from the ionization energy terminology, and that is called work function. And just it is defined as the energy required to take away the electron from the surface and raise it to the vacuum. So if you keep a metal in a vacuum and then try to remove electron from the surface, so that is called removing electron from the surface and taking to the vacuum level. So that is equivalent of what you called ionization energy for isolated gaseous atom. So work function is a constant for anything. So you know what you are getting if you are plotting kinetic energy, which is kinetic energy must be equal to this h mu minus phi. So that is what you are getting. You have a intercept on so intercept will give you the phi, the work function, and the slope will give you the slope is will give slope of this function. So slope of this will be, frequency is on the x-axis, kinetic energy on y-axis, so dy by dx is h. Is it will be h, and intercept will be phi, the work function. So that's how you can correlate this graph for understanding the basic things. So that's how we understand it. Energy required, so this is the energy required, which is defined as work function phi from a metal surface, and if h mu is less, nothing happens. No matter how many photons you provide of this energy, nothing will happen, the electron won't be ejected. But if the work function is this, the energy required to take out that sufficient enough to take away the electron, if h mu is much larger than that, the electron will be ejected, and rest of the energy, you see very nicely it has been shown through this arrow. The green arrow is the h mu, the large one, much carrying much energy than this one, and then the required phi, and so the electron is ejected and it moves. Rest of the energy is converted into kinetic energy, and it moves with that energy. So this is what happens when the photon is more carries more than enough energy to eject the electron, excess energy is carried away as the kinetic energy of electron, the photoelectron. So this electron which is ejected out from the surface is called photoelectron, and this phenomena can happen with any species, not just metals. You can have a molecule of any mm, uh, any kind of surface, not like a ionic solid, anything, and you can analyze the spectrum, any metal complex, metal ligand complex. So in all those things you can have this kind of phenomena where electron can be ejected if certain energy is given. So that is correspond. So that is what we know as ionization energy, is a familiar term that we have already known from early days. So when for an atom it is very simple, uh, but a molecule will involve a kinetic a molecule has, in addition to that simple uh, translational motion, it will have vibrational and rotational level. So for a molecule, when you are defining ionization energy, it is the transition from the lowest electronic vibrational rotational level of the isolated molecule to the lowest electronic vibrational rotational level of isolated ion. So we are talking about the energy difference between isolated molecule and isolated ion. So lowest possible state of each one of them is compared, and that difference is called ionization energy. And binding energy is a similar term. Uh, it is the energy change corresponding to ionization reaction, ionization which leads to formation of an ion. And if the configuration of ion is retained the same, the geometry is retained as in the neutral molecule, ground state, so that kind of situation is called, then the energy required to take away that electron is binding energy. So and the work function is the minimum energy needed to remove an electron from solid to a point in the vacuum. So as I told you, if you have a metal surface in solid, that is a solid kept in a vacuum, and then the energy required to take away the electron from the surface, so all around is vacuum, so you take in, so any point in the vacuum, when you raise that electron, that is work function. So these are three different similar sounding things, but slightly differently related, different slight difference were there. So similar but different. So this is the point of difference that I would have like you to know. I would like you to know. Um, so these three terms would be like, so as I told you, photoelectric effect is the basis, and so we have kinetic energy convert, excess energy is converted to kinetic energy, and we, the ejected electron, it is the kinetic energy that we have to measure. It is measured by a spectrometer. So you have to make a setup that can determine the energy of the electron, the photoelectron that has been ejected from the surface of a metal, or it has come out from a gaseous molecule, or anything like that. So ejection of electron from a neutral molecule, you can think of, so that is the difference between the so when the molecule is ionized, the photon, which is photon energy is known, so how much frequency you are giving, h mu is known, and what the when the this h mu, the photon with h mu energy impacts, it makes an impact on the surface, or makes an impact on a molecule, it the electron is ejected, and this kinetic energy is to be measured. and this analysis gives you the ionization energy in case of such isolated molecules if you have. So in such a case, when you have isolated molecule and you know this thing is known, uh, this is known prior to the experiments, what energy you are giving. So kinetic energy is to be determined by the spectrometer. So in this manner, you can determine the ionization energy, and ionization energy is the negative of ionization energy is the energy of the orbital. So energy of the orbital can be known in such situations. So energy of any orbital can be known if you provide the uh, h mu photon of right kind of energy, right value of energy. So this is the scheme that we can write in explicit manner for molecule M. The molecule is M, photon hits it, hits this molecule, which loses the electron. You analyze the kinetic energy of electron, and the difference between the photon's energy and the kinetic energy gives you the ionization energy. So this is something uh, that can be easily, very logically you can take it. Then the theorem that relates to the energies is called Koopman's theorem in photoelectron spectroscopy. This is the important part. Energy of molecular orbitals. So ionization energy, Koopman's theorem tells you that ionization energy is directly related to molecular orbitals, energy of the molecular orbitals, and in a more formal way we can say that it is the negative of the eigenvalue. So as I told you, the negative of the ionization energy will be the orbital's energy. So the theorem tells you that the negative of eigenvalue of occupied orbitals from the Hartree-Fock model is equal to the vertical ionization energy. So of course, ionization energy, the energy required to take the electron away, so it is a positive term, and you always know that all the orbitals energy are defined in a negative way. So hydrogen energy you have seen in atom case, each of the energies were with a negative sign, and the maximum when the n is equal to infinity in hydrogen, it was the energy value was 0. So that is how, so it's related to each other. So in a simplified statement, a simplified version of the same thing which was given above in a more quantum mechanical language can be simplified further, and it is stated as a, for closed shell molecule the ionization energy is equal to the orbital's energy or binding energy, equal to the orbital energy, that is minus, with a minus sign, ionization energy is equal to the orbital's energy, which is also called the binding energy. So photoelectron spectrum is a direct, you can get uh, direct knowledge about the molecular orbital's energy. So MO diagram can be very well correlated to all these energies of the photoelectrons that you obtain and then correlate it with the orbital's energy. It is possible to know each of the energy levels experimentally. Uh, so so there are also other things that you can learn from this photoelectron spectrum, that sometimes the ionization of a molecule can change the geometry of the molecule. So that can also be learned by careful analysis of the photoelectron spectrum. We will see that in later on in the course of this uh, class. So we will see that if the electron is removed from bonding orbital, anti-bonding orbital, non-bonding orbital, the changes would occur. As you can imagine, if you are removing an electron from bonding orbital, the bond strength will become weaker. If you are removing electron from anti-bonding orbital, the bonds will become stronger, and so you will observe a change in vibrational frequencies that you can directly correlate. So that we will see that you also get vibrational fine structure in photoelectron spectrum, and that helps you in understanding all these finer details. So what is, so when we start this spectroscopy, we have need to have a source of light, and so it must be energetic enough to excite, not just excite, to ionize the electrons, to take away the electron, not a simple excitation of one level to another, but you can imagine of excitation from n is equal to certain specific values, occupied energy levels at room temperature, to n is equal to infinity, or you can say about n vacuum level for the. So this is to be done. So first thing that we can think of, so how do we irradiate the sample? So source, you need a source to irradiate, excitation source, uh, and then you also, the electron will be ejected, photoelectron. You need to analyze the kinetic energy. So that is part of a analyzer and a detector system that you will have. So you also need to create a high vacuum so that there is no other thing present, otherwise kinetic energy of the ejected electron will be affected due to the disturbance that is there, like air or anything. If it is any so air contains gas molecules, so all those should not be there. They should be perfectly, there should be no gas particles in the chamber where electron is traveling, so that you get correct measure of the kinetic energy. So simple block diagram to understand the system is that you have a source, then so ionization chamber, so light falls on the sample here, and so your molecule or sample is here, and it gets ionized. The electron travels and it is analyzed by electron kinetic energy analyzer, and the detector finally is converts that signal into uh, a signal that is can be read and plotted on the computer. So it is electric, it converts it into electrical signal, which is further connected to this computer amplifier. And so you can see that all these things, a high vacuum is created by, in all these chambers, radiation source, ionization chamber, analyzer, detector, all are connected to a vacuum pump. So you are trying to create an environment where the electron which is ejected is it is, it doesn't hit anything unwanted, any unwanted gas particle which may be present. So you have to avoid that, any presence of any gas particles in any of these compartments, and so it is connected to vacuum. So a design is here. So UHV means ultra high vacuum. Ultra high vacuum is UHV chamber, this spherical one. This is the source, X-ray source, X-ray source or UV. So these are the two methodology that is being used nowadays for photoelectron spectroscopy, either ultraviolet light source or X-ray source. So X-ray, if you X-rays are more energetic, X-ray is having much higher energy than um, required, and it will eject out the core level electron, even the core level electron, not just valence electrons, also the core level electrons will be ejected when X-ray source is used. Ejects this will eject electrons from the core level, or inner, you can say that inner shells. UV, this will eject the electron from valence shell. So this is these are the two different. If I define photoelectron spectroscopy, we'll have two different types of photoelectron spectroscopy that will be discussed in due course of time. So these are the things. The source will be different. You can analyze the same sample with a different point of view to understand the bonding aspect, to understand this. Um, you use the UV light so that you get about the energy levels of the electrons. You get the idea of energy levels of the valence shell orbitals. So the energy that scale that we are talking about here is around 200 to 2000 electron volts X-ray, in case of X-rays, to examine the core levels of electrons. So you can see the inner shells, the extreme very close to the nucleus, the electrons which are very close to the nucleus, even that can be ejected using X-ray photoelectron spectroscopy. In short, we call it XPS. And the other form that we call much in comparison to that, you can think of this 10 to 45 electron volts. So it is much less energy that we are giving in when we perform this kind of spectroscopy, and it will help you in ejecting the valence level electrons, so you can get idea of the valence shell orbitals. So it is a you have to use a monochromatic light source, ultraviolet. So if you're talking about UV photoelectron spectroscopy, ultraviolet light which ionizes most of the gases in an ionization chamber. So it is a light source that is used usually is the helium-1 584 angstrom, or you can say 58.4 nanometer, which corresponds to 21.2 eV. So this energy is sufficient enough for ionizing most of the molecules. And so when this is the in a typical UV-PES, it is the helium-1 line that is used as a source of light. Or so so this gives you idea about if you want to understand the bonding orbitals, what kind of orbitals are involved in bonding for that particular system. You can do that using this kind of technique, valence shell, and you can learn about the highest principal occupied quantum numbers of atomic orbitals. So if we label them as J, each atomic orbital, each one of them will have characteristic binding energy, and the minimum energy required to eject them to n is equal to infinity, that level is the binding energy that we are talking about. So h mu, and if that species happens to be the atom, not a molecule, then we call it ionization energy, in simple terms. So that becomes ionization energy when we're talking about a simple atom. So kinetic energy is h mu minus IEJ. So the photoelectrons are separated according to their kinetic energy in electron analyzer, and then detected and recorded. So you will have a peak at each of the energy h mu minus So in terms of kinetic energy, you are plotting all the electrons. So the graph will look like something like this. An ideal photoionization process and the photoelectron spectrum is depicted over here. So this is so if you have electrons over here, you see this is electron, and these are two energy levels in a molecule, and if you give, so look at this, and you are providing, suppose the h mu, the photon hits one of these electron, it will be ejected, and so it will be ejected with so the energy required to eject this electron is this much, rest of it will be kinetic energy. So so the rest of it, this is the um, energy. So this is up to this 0 0 line is the ionization energy 1, okay, and then rest of it, the h mu part will be equal, so it will be kinetic energy of the ejected electron, ejected electron. So this is this part that you are getting. So if you are plotting it, you will get a peak here, sudden in the detector will show a peak because the electron has come, so the current will increase, and that and detector, and you will get a signal and a jerk, and at that point, so corresponding to a particular value of energy, you will get a signal. Then you move to the analyzer to a next higher, just a moment. So you can see this, so this one, what I was, no, it's gone. So this starts cutting it, ये कटने क्यों लग जाता है. So as you can see here, again this is, so as you can see here, so this level defines the energy required to take away the electron. So energy required to take away the electron is this much, I2. Energy required to take away this electron is this much, I1. Okay, so and so once the electron, so and you are hitting this molecule with the same h mu, same energy, so rest of the energy will be converted into will be as kinetic energy of the electron. So you have kinetic energy of 1 here, this appearing over here, and then for the second electron also you will have kinetic energy 2, second kinetic. So different energy channels you can have, and you can analyze at this point. So not this one only, so this part is appearing here, this one appearing here. So two on the spectrum, you will for typical photoelectron spectrum will be appearing as uh, a plot of this thing, kinetic energy, something like this. So corresponding to kinetic energy, so photo, so first one ke1 will appear here, and ke2 if kinetic energy is, so how, as the number of electron increases, this intensity will go on increasing. So number of electrons is more, at the same place you will have greater intensity, so that is the current will increase when that particular energy channel is applied. So that kind of thing happens, and that's how we obtain a spectrum. If the species So that is for an atom. This scheme, simplest scheme, is for the atom. And if you have a molecule, then it becomes slightly more complicated, because instead of the kinetic energy, in addition to the kinetic translational kinetic energy, you will also have changes in the vibrational or rotational energy. That is another possibility. So so that also has to be taken into account. So in this particular case, the kinetic energy that you observe will be h mu minus ionization energy minus the vibrational and rotational energy of the excited state, E star. So vibrational and rotational energy of the excited state, that has to be deducted, and then you can talk of the translational kinetic energy. And so that is the basis. The translational kinetic energy of the electron, ejected electron, is to be analyzed. And to do so, we must deduct this part, the vibrational and rotational, which is also a type of kinetic energy, which is a different form as compared to the free electron. Okay, so some of that energy is imparted to the molecular cation that will be formed due to the taking away of that electron. So in this kind of spectrum, you will also find vibrational lines for each type of electron ionized. Because if you analyze the energy of the that orbit molecule and the cation that is formed, जब भी इलेक्ट्रॉन निकलेगा तो एक cation बनेगा. सो फोटो इलेक्ट्रॉन स्पेक्ट्रम में हमेशा एक कैटायन बन रहा है और एक इलेक्ट्रॉन निकल रहा है. इलेक्ट्रॉन जो निकल रहा है उसकी एनर्जी को हम एनालाइज कर रहे हैं. ठीक है. तो एटम के केस में बहुत सिंपल था कि सारी की सारी जो एक एनर्जी है एच म्यू माइनस आयोनाइजेशन एनर्जी को छोड़ के बाकी की सारी जो डिफरेंस एक्सेस एनर्जी थी एच म्यू में, वो सब काइनेटिक ट्रांसलेशनल काइनेटिक एनर्जी में कन्वर्ट हो रही थी. लेकिन द मोमेंट यू हैव अ मॉलिक्यूल, the same excess energy may also be used up in raising the vibrational and rotational energy of the molecule. So that will not show up in the kinetic energy of the electron. So um, so that has to be taken care of when we analyze this kind of spectrum. So we get a band, we get several lines depending on at the instant of when the electron was taken away, at what vibrational energy, at what rotational energy the molecule was having. So accordingly the kinetic energy will be affected, and you will get a wavy pattern, and slightly so, several lines will appear around around a main peak position. So that is what we analyze minutely. So other than Koopman's theorem, there are certain rules that we also follow, um, that is also obeyed in this kind of spectra. So one is that each band in the spectrum corresponds to ionization from a single molecular orbital, number one. Each band. So we get in case of molecules we get bands. In case of atoms we get lines. One line for one particular orbital. But here for one molecular orbital you will get a band, because in one molecular orbital, when you're talking about a molecule, one electronic energy level contains rotational and vibrational level. एंड उस समय मॉलिक्यूल किस वाइब्रेशनल और रोटेशनल लेवल में था, उस पे काफ़ी कुछ डिपेंड करेगा. एनर्जी रिक्वायर्ड फॉर what is the energy required to take away the electron, and slightly different line would appear, and a collection of such lines would appear as band. So each second point is that that is observed in this spectroscopy is that each occupied molecular orbital of binding energy less than h mu gives rise to a single band in the spectrum. So first point, each band in the spectrum corresponds to ionization from single molecular orbital. Each occupied molecular orbital of certain binding energy that is less than h mu gives rise to a single band in the spectrum. So these are simplified rules. They help you understand. So we'll take some examples and then we'll understand all these points. Uh, so sometimes more than expected bands do appear, and the reason for that is that additional bands come from simultaneous excitation of two electrons, second electron to an unoccupied excited state. So that also sometimes appears. So that is a two electron process, and so when the ionization potential region below 20 electron volt, the bands mm, so they are much weaker. These two electron processes are much weaker in signal. The signal intensity will be much lower in, for these things. Second thing that is that ionization from a degenerate occupied molecular orbital can give rise to uh, many bands depending on the orbital components. So that may happen because you have to look at the energy levels of both the molecule from which you are taking away the electron and the energy levels of the cation, positive ion that will be formed. So if there is difference in that, so suppose that there was a degenerate set molecular orbital, and now in the once the positive ion is formed, that they are no more degenerate. Then in these cases, you will have more than it can give rise to many bands more than expected, uh, and then so this mechanisms, the mechanism that remove the degeneracy, spin orbit coupling and Jahn-Teller effect. We have learned about that, and we'll see more about spectral. Third, we will also find that such as when we have simple O2 or NO, in these cases you have unpaired electrons. So oxygen has unpaired electron, NO has unpaired electrons, and in such cases we can again get more bands than there are as compared to the occupied orbitals in the molecule, and we'll see why it happens with some examples. So the first example that we are taking is the spectra UV visible, sorry, UV photoelectron photoelectron spectra of atom. So this is for with using a helium-1 source, 584 angstrom, that is 58.4 nanometers. This is the spectrum that is obtained for mercury when Hg is converted to Hg to Hg plus. This is uh, so when this is done, so you can see the x-axis. You have immediately below it you are seeing electron energy. So this is the kinetic energy of electron plotted, and you get signals according to a small signal appearing over here, something like this appearing over here, and the maximum at corresponding to this. So when you analyze this, you can you know the spin orbit coupling, you have understood that. So accordingly you can find out uh, which one, how you can assign the bands, assign the signals that you obtain depending. So for example, in the previous slide you have just seen that mercury atom was excited by that radiation, uh, UV light of 58 angstrom. uh, Absolute. So it is the in photoelectron spectroscopy we should understand one thing, that it is the relative signal intensity of one peak with respect to another peak that is more important than the absolute intensity, because there are many factors which can alter the absolute intensity, but relative intensity would be same if you analyze from one system. The same molecule analyzed in two different spectrometers will have same relative intensities of the uh, appearing from different orbitals. Absolute intensity will be different, so it is most important thing is that you analyze the relative intensity of the peaks, which is more meaningful. So we are going into in that direction, and so electron volts are used for the energy, that kinetic energy that we are using, or something. Mm. So potentials and potential energy, sorry, electron volts, you can all you can sometimes volt is also used. You can always convert although it is unit of potential, and electron volt is units of energy, which it is can be interconverted, and because it is the raising the electron through 1 volt is imparts 1 electron volt of energy. So using that relationship you can always analyze that. And so what we saw in the previous slide we can just put in here. So the spectrum that we obtained is the spectrum kind of spectrum that we obtained, uh, one energy, so only one energy of electron appearing in the detector at one time. So this is called differential form of spectrum. There is also another form that is encountered in this spectroscopy, that is called integral form of the spectrum, in which all electrons of different energies can reach the detector simultaneously. This is the integrated form, and so integrated form is, I think, here. Yeah, this is integrated form of. So this will appear like steps. All electrons, when they are allowed to approach the detector at the same time, so for the same set of uh, electrons you are getting this kind of spectrum, step like format that is there. And so just little bit about this I can tell you, that what we see here. So in Hg plus ions are formed because of the ionization, and if you look at the scale, there's 10.44, 14.4, and 16. So the three lines are observed, and these three correspond to the three different spin orbit states that you can define. Okay, so the neutral atom, what you have, the configuration is 5d10 6s2 in the outer shell, and the designation is 1s naught. The 2s half is the state of Hg plus. So labeling is being done. What you saw in the slide, the labeling of the states was done with respect to the cation, the positive ion that is formed. So one of that state is 2s. So starting from 1s naught, you are getting this state with ejection of electron from the s orbital. If 6s electron is lost, but if the electrons are lost from d 5d, then you will get both of these. So if you have, what we see here is that electrons, you have, so what I was telling you is that you have 5d10 6s2. So 6s2, so this electron should appear here, lowest energy. Then these two 5d10, these three, these two peaks you are getting from when the electron is ejected from this particular thing, uh, any of the d orbitals, you will get these two patterns. So you can see the energy, kinetic energy decreases as the energy required to take away that electron is increasing. So ionization energy, it is easier to take away 6s electron, so it will have the highest kinetic energy. Okay, सबसे कम एनर्जी चाहिए 6s इलेक्ट्रॉन को निकालने के लिए, तो उसमें से जो इलेक्ट्रॉन देखिए ये 11 पे सबसे हाईएस्ट काइनेटिक एनर्जी पे अपीयर हो रहा है, हाई काइनेटिक एनर्जी, kinetic energy, and the d electrons which are inert, lying inner to the outer shell, they are having low kinetic energy because the wavelength used is same, the source radiation is fixed, h mu is fixed, so h mu is fixed, right? And so if you're talking about, so जिसमें कम एनर्जी लगा वो उसकी काइनेटिक एनर्जी ज़्यादा है इलेक्ट्रॉन की, and you can see the signal intensity of the signal is high because d electrons is having d10, 10 electrons are able, the probability of d electrons getting ejected is more, and accordingly you will get higher signal if you add these two things. So these are appearing in the proportionate terms if you analyze from the spin orbit coupling point of view. So you have produced, so the two d states that we were talking about are produced by the 5d electrons. 5d electrons produce these things. 5d10 tells you, takes you to these two states in the G plus, and that's how the leveling is done. And this is the integrated intensity, so it is cumulative, it takes cumulative things. So the electrons here are showing overall integrated form of graph is this. In this case it is the step height that shows the difference. So if you see the difference between the step heights, so this is the difference in the signal that you obtained in the previous one. Okay, so the ratio of intensity is still the same, only thing is the form has changed because it is integral form of thing when all this thing are appearing at the same time at the detector. In the previous case the spectrum was obtained when the electrons were reaching the detector one by one of certain kinetic energy. You apply a filter, allow only certain kinetic energy to appear at the detector and the others are blocked off. So that was the differential form of spectrum. This is the integral form of equation where all of them are allowed at once. So this is the notations that is followed. Okay, we'll make it yeah, we'll do it in the next class, I think. So this is simple terminology that we will use to denote from where you have taken away the electron, from where the electron has been ejected, कहाँ से इलेक्ट्रॉन निकल के आया उसके करस्पॉन्डिंग सुपरस्क्रिप्ट देते हैं, इलेक्ट्रॉन orbital from which the electron is removed, superscript and -1. So like we have discussed 5d10 6s2, so electron if it is removed from 6s we write 6s minus 1 ionization process. It is 6s minus 1 is the superscript. Similarly 5, if the electron is taken away from the 5d subshell, then we write 5d minus 1. So from the point of view where from you are taking the electron away, so that is uh, so because of so Koopman theorem and the one band per orbital, that theory is gone here because you are having spin orbit coupling in this case, but you can clearly so if you understand spin orbit coupling, you can still analyze it very well. So a similar splitting is possible whenever an ionic state has both orbital and spin degeneracy. So we'll see more about this in the next class. Yeah, we'll analyze the more. So we have started with atoms, and we will talk about diatomic molecules such as N2O2, H2, and photoelectron spectra. Then we move to the more complex molecules and how the geometry can change. So until that, there is no change in geometry and something like that, because diatomic molecule will always be a linear molecule. So things will appear more intricate when we move to the next part, having non-linear molecules. So that's all for today.